Hi, I'm Mike Seeds, and we need to talk about modern optical telescopes. Since the time of Galileo, astronomers, like pirates, have been identified with the telescope. Over the centuries, astronomers have developed lots of different kinds of telescopes, but the optical telescope that focuses visible light is still king. You know from your reading that the best astronomical telescopes are reflecting telescopes because they don't suffer from chromatic aberration. And you know that the bigger a telescope is, the more light it can gather. That's important for astronomers, but not so much for pirates. Astronomers look at really dim things in the sky, so they need as much light as they can get. So how do you build reflecting telescopes that are as big as possible? That's the key question we need to talk about. Here's a cutaway diagram of a traditional astronomical telescope. Starlight enters from the upper right, goes to the bottom of the telescope tube where it reflects off of the front surface of a concave mirror called the primary mirror. The converging light then travels to the top of the tube where it reflects off of the front surface of a smaller mirror called the secondary mirror. The light then goes back down through the tube, through a hole in the middle of the primary mirror, and comes to a focus at the Cassegrain focus. Here's an image of a big telescope from the 20th century. The primary mirror is 4 meters in diameter inside the bottom of the telescope tube. The secondary mirror is at the top, and the light comes to a focus in the Cassegrain focus inside the instrument cage at the bottom of the tube. Notice the astronomer for scale. Big, thick mirrors had big, tough problems. As the telescope moves around the sky, the primary mirror can sag. So the mirrors needed to be made very thick, but that makes them heavy. Some can weigh tons, and those big, thick mirrors are slow to cool off in the evening air. If a mirror is warmer in some places and cooler in other places, expansion can distort its surface and blur the image. These big, heavy mirrors are things of the past. Computers have given astronomers new ways to focus starlight. For one thing, computers have simplified the mountings that support telescopes. As Earth turns eastward, the sky moves westward, and astronomical telescopes have to move westward to track the stars. Traditional telescope mounts had one axis, the polar axis, parallel to Earth's polar axis. And as Earth rotated eastward, a motor called the sidereal drive would move the telescope westward to follow things in the sky. You can imagine that it was difficult to support a big, heavy telescope on such a complex support. And it was really expensive to mount big telescopes on such complicated machinery. Modern computers are fast enough to control motors on both axes of an alt-azimuth mounting, moving from right to left and up and down like a cannon. Thanks to the computer, the telescope can move smoothly westward to counteract the rotation of Earth and track a star. This kind of mounting is stronger and less expensive to build. Grinding a telescope mirror is a delicate and slow process, and supporting the mirror so it doesn't sag under its own weight is complicated. Modern astronomers have used computers to monitor grinding of telescope mirrors, and once the mirror is installed in a telescope, to control the mirror supports. Some big mirrors are thin glass discs called floppy mirrors. They're supported by thrusters under the mirror that are connected to a computer. The computer monitors the image formed by the telescope and continuously adjusts the shape of the mirror. Another way to solve the problem is to make really big mirrors out of rigid hexagonal segments, each ground to precise shape. Computer-controlled thrusters under the mirror segments keeps them aligned to produce a single precise surface to focus the starlight into a sharp image. The biggest telescopes in the world are now made with segmented mirrors. In this image, looking down on a giant segmented mirror, you can see the hexagonal mirror segments in the jagged edge of the mirror. The faint hexagonal pattern of the segments is just visible on the surface of the mirror. Whether a mirror is a single floppy mirror or a segmented mirror, the technique is called active optics because the computer must actively control the shape of the mirror. The advantages are huge. Such a mirror weighs much less than a traditional telescope mirror, and it cools quickly in the night air. For example, the two Keck telescopes on a mountaintop in Hawaii have segmented mirrors 10 meters in diameter. Computers control the segments, making them two of the leading telescopes in the world. The newest large telescopes now being built will all have segmented mirrors.